Unit 6, Day 8, Transforming Exponential and Logarithmic Functions. Today you will transform exponential and logarithmic functions. The parent function for a family of exponential functions depends on the base. The domain is from negative infinity to positive infinity, and the range depends on a particular function. Exponential functions have a horizontal asymptote. These also will give you a graph that looks like a curve. Example number 1, for the function f of x equals 3 to the x power, the first thing that they want you to do is make a table. So make an xy table. Let's try values -2, -1, 0, 1, 2, and plug these values into your calculator. So when you raise 3 to the negative first power, you get 0.333 repeating. When you raise 3 to the negative second power, you get 0.1 repeating. 3 to the 0 power equals 1 whole. 3 to the first power is 3, and 3 squared is 9. So we need to plot enough of these points to see what's happening. So -2, it's very close to the x-axis. -1, it's still very close to the x-axis. When x equals 0, y equals 1. When x equals 1, y equals 3. When x equals 2, y equals 9. So you can see that our graph is increasing at a very quick rate. If we identify the domain and the range, the domain is looking at the x values. So we want to say, where is the smallest x value, where is the largest x value that our graph is approaching? And we can see it's going from negative infinity to positive infinity. Our range is looking at our y values. We can see that it's approaching 0 but not touching it. So we can say it's from 0, but we don't want to include that point, to positive infinity because it goes on forever. Graphs of exponential functions can be transformed as we have done with other functions. Our a is going to, if our a is less than 0, it's going to reflect across the x-axis, so if it's negative. Our b is the base, and if b can be greater than 0, b can be greater than 1, which makes it increase. B can be between 0 and 1, which would make it decrease. A vertical translation is our k on the outside, and that if it's positive, it moves up. If it's negative, it moves down. And we have a horizontal asymptote where y is equal to k. And then when we look at our h inside up by our exponent, it is the translation right and left, so it's going to go opposite of what you think. If it's negative, it's going to move to the right. If it's positive, it's going to move to the left. In example 2, it says use the graph of f of x equals 2 to the x power as a guide. So that's going to be our parent function, and we're going to describe the transformation and graph each function. We also then are going to state the domain and the range. So if we start at 2 to the x power and we have a -3 on the outside, it's going to move our graph down 3. So if we translate our points down 3, 3 is going to become our new horizontal asymptote. So our graph's going to approach 3, approach -3 but not touch it, and increase. If we state our domain of our function, we're looking at our x values. It's going from negative infinity to positive infinity. Then when we look at our range, we want to look at our highest and our lowest y values. It cannot touch -3, so we'll put in just a parenthesis, and it goes on and on forever to positive infinity. Looking at example 2, we have a negative out front, so that's telling us that it's going to flip our graph over. So if we visualize our graph flipped over, we are working with something of this nature. So we can say flip over x, And then this 4 up here is going to move 4 to the left. So we then can transfer 1, 2, 3, 4 points to the left. And we can then draw our graph on our paper. So looking at our blue graph, that is our correct graph. If we state our domain and our x values, you can then again see it's going from negative infinity to positive infinity. If we talk about our range or our y values, it's approaching 0 but not touching it. So we want to use a parenthesis, and it's going on forever towards negative infinity. Looking at example A, we are now transforming from the graph 1/4 to the x power. So my -2 is going to move my graph down 2. My -1 and my exponent is going to move right 1. So if I translate my points down 2, right 1, we can see that our graph is approaching -2 but not touching it. So when we state our domain, it's still negative infinity to positive infinity. And my range is approaching -2 but not touching it, and it's going to negative infinity, or positive infinity, excuse me. When we look at example B, we can see that our -1 flips over the x. So it's a reflection. And then our 1 here is going to move it up 1. So if I flip this point over my x and go up 1, my graph's going to be here. The point -1, 4, if I flip it over my x-axis, move it up 1, we can see that our graph's approaching +1 but not touching it. Our domain is negative infinity to positive infinity. Our range is going towards negative infinity and approaching 1, but it's an asymptote, so it will not cross 1. In example 4, the graph g of x is translated 5 units down and 7 units to the left from f of x equals 4 to the x power. So to write the rule, we write g of x equals 4 to the x power. 7 units to the left means we put opposite up here, x plus 7. 5 units down, we put a -5 on the outside, and you just wrote this function. Looking at example 5, the function f of x equals 2 to the x power is shown at the right, and it passes through the points 0, 1, 1, 2, and 2, 4, as you can see on the graph. Recall that the inverses have the x and y values interchanged, and their graphs are reflected over the line y equals x, which you can also see on the graph at the right. We want to use these facts to graph f of -1 to the x on the same axis. So we want to graph our inverse. So we can either look at our ordered pairs and switch our x and our y values to graph our function, or we can simply draw the line y equals x and reflect our points over that line in order to graph our inverse function. So f of -1 of x, our inverse function, is graphed in red. And then if we wanted to state the domain of our inverse, our x values are going from negative infinity to positive infinity, and our range is also going from negative infinity to positive infinity. The next slide is just information. The inverse of an exponential function is called a logarithmic function. The parent function for a family of logarithmic functions depends on the base, denoted by the subscript on the word log here. So your base, remember, is this little number at the bottom. The domain depends on the particular function. The range will always be negative infinity to positive infinity, so you can tell logarithmic functions are inverses of exponential, and we just graphed exponential functions. Our domain was always negative infinity to positive, so because those switch spots, that makes sense. Logarithmic functions have vertical asymptotes instead of horizontal. We graph logarithmic functions using the same transformations that we've used previously. Our a reflects over our x-axis. Our h translates left to right. Our k translates up and down. And our b, which is the base, determines if it's going to be increasing or decreasing. So if we use f of x equals log with the base 3 of x as a guide and we describe our transformation, this 1 inside here would mean it moves right 1. This 2 would mean up 2. So if we find some points on our graph and we move up 1, right 2, we can graph our new function. So it would be approaching 2 but not crossing it. Our domain would be our x values. It approaches 2 but does not touch 2 and goes to positive infinity. Our range is what they said on the previous slide, negative infinity to positive infinity. Looking at this next example, this negative is going to reflect over the x-axis. It doesn't move left to right any, but it moves down 4. So if we reflected this over our x-axis, our graph would look something like this. And then if we move that down 4, you can just transfer those points. And you graphed your log function. The domain would be approaching 0, not touching it, to infinity, even though it appears my line kind of crossed it. And then our range would be negative infinity to positive infinity. The last example, the graph of g of x is a reflection in the x-axis with a translation 2 units down, 4 units left from the graph of the function f of x equals log with the base 8 of x. Write the rule for g of x. So g of x equals a reflection over the x-axis makes our log negative. Our log with the base 8 stays the same as if it's a parent function per se. We're going to move left 4 by putting x plus 4. And then 2 units down, we would have a minus 2 on the outside.